And of course, you can tilt or turn this scheme to adapt for a boundary that is upstairs or on the left side or downstairs. So with this, we can handle basic boundaries, an electric wall, a magnetic wall, and we can solve a problem still with the same kind of media inside. Now, I should possibly tell you why this method has been so attractive and so much used to solve electromagnetic fields some 50 years ago. And the reply is more or less this. In fact, engineers or mathematicians have used something that has already been there. At the time of 1970, there have been big mainframe computers. You still do not have your PC on your desk, but anyway, you had a terminal to a big room full of electronics, which was a big computer. And those computers already have had implemented software for solution of electric networks. Those things have been mostly organized using netlists. So you had, for example, in order to represent a circuit like this, a resistor and a capacitor, you would have a netlist. You had node 1, node 2, and node 0. And in order to put this into the computer, that would be something like circuit A, and then you would put from node 1 to node 2, resistor 100 ohms. From node 2 to node 0, capacitor 10, which would mostly mean 10 picofarads. And of course, there would be an end of the block. So this was the language that was used by the computers, and there have been already programs to solve DC, transient, or any analysis of such circuits given by a netlist. And now the equivalent of this situation, the network equivalent of this situation, is a grid where you have node voltages or nodes, and this element could be replaced by a transmission line section, which connects the 2 points, and the length of the transmission line is just chosen so that the propagation from here to here is the time of propagation of the signal through that piece of transmission line. Then, of course, you could do this as a list, a net list of transmission lines, and pass that to the computer, which somehow solves that. Of course, you had to put down the netlist, so there have been specialized programs called preprocessors that took your specification of shape and converted that into a netlist and sent to a big mainframe computer to solve. But the solution itself was at no cost. Then mostly another program called postprocessor took the values and pictured that like equipotentials or waveforms or wavefronts or anything. Now, this needed a piece of transmission line between the two nodes, which served as a time delay. The time delay introduced in original case, in the original problem, by spacing in a material that the wave would have needed some time to travel through, and in this case it has been substituted by a section of a transmission line. So now if there was a dielectrics, say with relative permittivity of 4 and another area of problem with lower relative permittivity, we would have a problem with finding a transmission line that would enable us to slow down the propagating signal. But that has been achieved using a stop instead of the line, what a stop is. So you have a transmission line and you cut it and put here another section of the transmission line of a proper length, so that the wave that travels through the line has a longer path. Of course, you have to terminate this somehow. You could terminate the stop by open or short. Neither of those terminations conserves any energy, so the whole energy is reflected back and gets from one node to the other node, but it takes longer to get there. So by using a line loaded by a stop instead of a transmission line, of a pure transmission line, you could easily tell to that computers, to that programs that have been solving circuits, you could easily model different properties of the material. So in fact, this method, transmission line matrix method, relied on circuit simulators and converted an electromagnetic problem into an equivalent model that has been composed of transmission line sections used in the most used dielectrics or material in the problem, and line sections with stops that have been used to slow down the wave in more dense materials. And then the problem of electromagnetic field has been converted into a problem dealing with voltages and current in an electric circuit. In an electric circuit that has been quite dense and had many nodes, but the programs have been designed to handle that. As you can imagine, the method has been used to solve a number of problems, and then somebody, a gentleman called Yi, invented finite difference time domain method that has been producing solutions not relying on circuit solvers, and there have been a lot of papers comparing those two methods, and at the beginning it seemed that the finite difference time domain method is much better because it offered more solutions. In many cases it found more solutions to the problem than finite difference time domain. Then again, there was a paper that investigated and compared several cases and has shown up that yes, transmission line matrix gives you more solutions. Unfortunately, any of those solutions in addition to FDTD are non-physical, are false results due to discretization and solution methods. Since then, transmission line matrix is not very much used, and the kingdom has came to finite difference time domain method, and that is what I would like to tell you about transmission line matrix simulation at the moment. So please, any questions? Well then, for the next case, next lecture, we would talk about a numeric solution of a case that has nice analytic solutions for an ideal conductors, ideal dielectrics, but we will try to solve a real situation within a plane waveguide where all materials would be lossy and the field could leak out of the waveguide. So we will do a numeric method that is capable of handling that. The main lesson learned from that would be the solution technique, not the results itself, because normally you would ensure that your waveguide has solid metallic walls that do not leave the wave out. But anyway, just to have a tool for solution of complex structures and to show some tricks, we will do that in the next lecture, which would happen on next Tuesday, which is the 23rd of March. Gentlemen, it's been a pleasure, and see you next week. Bye.
Thank you.
See you
Goodbye.
next week. Thank you very much.